chemical equilibrium, level 1 and level 2 problems. In our first problem, we're going to look at the decomposition of hydrogen iodide to form hydrogen and iodine. Notice everything's in the gaseous state, which will be useful when we get ready to write our mass action. Because both initial and equilibrium values are provided, we'll refer to this as a level 2 problem. Notice the size of the container is provided. It is a 1 liter container. Why is this needed? When you get ready to plug values into your mass action, they need to be in molarity, that is moles per liter. So to set up our equilibrium chart, we want to make sure that everything is in molarity. So we're going to take the quantity, the moles, divide it by the volume of the container size, liters, and you'll have the molarity values needed for the mass action. So let's take this information and place it into the chart appropriately. We are provided with one initial value, that was for the reactant, and we're provided with 2 equilibrium values for each product. Now, if one initial value is provided and nothing else is said about the other initial values, you can assume that you didn't have any, that it's 0. So let's go ahead and get everything in molarity. It is, let's go ahead and divide the moles by the liter. Go ahead and place the zeros in for the other initial values. So for the hydrogen and the iodine initially, we didn't have any. So we're going to place zeros there. Now how do you go initially when a chemical reaction gets started from not having any to having a certain amount of equilibrium? Well, obviously you have to add a value. So how do you go from having nothing to having 0.14? Well, obviously we had to add on the product side 0.14 for each of the products. Now if you're adding on one side of the double arrows, you must be subtracting on the other. That is, you cannot create something out of nothing. So if we're adding on the product side here, we need to be taking away on the reactant side. Now how much are we going to get to take away? Well, if you take a look at this, either the hydrogen or the iodine can allow you to calculate how much of the HI is actually going to be decomposing, the change amount. What do you need to focus your attention on? On the coefficients that balance the equation. The ratio between the reactant and either one of the products here is 2 to 1 for the hydrogen iodide to the hydrogen. It's also 2 to 1 between the reactant and the second product. So either one of these that you compare, it is a 2 to 1 ratio. So this means you subtract twice the amount that you're adding. So either one of these, if you double 0.14 or double this 0.14, it says that we're going to be able to subtract 0.28. And one thing I did not do is simply add the 0.14 values in the change part and get the 0.28 to subtract. I did not take the product side and add those two values to know what to subtract. Where I did focus my attention is on the coefficients that balance the equation. This 2 to 1 ratio says that we need to double this 0.14 to subtract the 0.28. We could have also looked at the 1 to 2 ratio between the iodine and the hydrogen, which also would have said we need to double the 0.14 to subtract the 0.28. It is just coincidental that those two values added together to be 0.28. Once you know how much you're subtracting, go ahead and subtract and you'll have your equilibrium value. It is this set of information, these equilibrium values, that we can plug into our mass action. If you recall, a mass action is nothing more than the ratio of the molarities of the products over the reactants, with each one of the reactants and products raised to a coefficient that balances the equation. So let's write our mass action for this chemical reaction. Products over reactants. The two products here are the hydrogen and the iodine. There are coefficients of 1 in front of both. So both of these are raised to the understood 1 power. The reactant here, the hydrogen iodide, goes on the bottom part of the mass action. Why are we squaring the HI? Because of the 2 in the balance equation. Once you have your mass action and you're ready to calculate your equilibrium constant, your Kc, you have to plug in equilibrium values. To calculate an equilibrium constant, Kc, you must plug in equilibrium values. So if we plug in our equilibrium values to our mass action, we'll be able to calculate our equilibrium constant. Notice that our Kc value here is less than 1. It simply says at equilibrium, when the rate of the forward equals the rate of the reverse, that this particular reaction favors the reactant side. A K value less than 1, equilibrium favors the reactants. A K value greater than 1, it favors the products. The next problem we're going to take a look at is a little bit easier. It is a level 1 problem. Why a level 1? Because all equilibrium values are provided. No initial values were stated, only equilibrium. Now they'd like to know the equilibrium values here for A and B, and the equilibrium constant here, Kc, is given. So by plugging this information into our mass action, and the equilibrium values that we do not know, letting them be represented with an unknown, with an x, we should be able to algebraically solve for the concentrations of A and B. So since everything is given at equilibrium in our equilibrium chart, we can place the one equilibrium value that is provided, the 0.5 for the product. No initial values were provided here, but they would like to know what is the equilibrium concentration of A and B. Since we do not know A and B, we can represent both of those with an x. Since it is a 1-to-1 ratio between A and B, we get to represent A with a single x and B with a single x. Now since the equilibrium constant value was provided, Kc, we're going to be able to plug these equilibrium unknowns and the one equilibrium value into our mass action and algebraically solve for x. When we write the mass action, remember it is a ratio of products over reactants. The C here is the product. Why are we squaring it? Because the coefficient in the balance equation in front of the product C is a 2. Notice that the reactants A and B go on the bottom part of the mass action, and they're understood 1 in front of A and B, the coefficients. So in the mass action, it's understood to be raised to the first power. Now let's plug in everything we know. We know the C value, the Kc value was provided, and we're going to be able to fill in A and B with x. So now what we have to do is we have to algebraically solve for x. Now notice that we have 50 is equal to 0.5 squared over x times x. Now to simplify this, one thing that we're going to learn that you can do in a lot of equilibrium problems is take the square root of everything. And this simplifies the algebra in a lot of cases. Sometimes it may complicate things, and it's not the way to go about solving for x. But in this case, we can take the square root of everything. If we take the square root of 50, it's just going to be 7.07. Taking the square root of 0.5 squared is going to get rid of the square. So the square root of 0.5 squared is just 0.5. And if you take the square root of x times x, or x squared, it leaves you with a single x. So let's take the square root of everything. And by doing so, once again, the square root of 50 is a 7.07. The square root of 0.5 squared is just 0.5. And the square root of x times x, or x squared, is a single x. Now, if you place the 7.07 over 1 and cross multiply, you should be able to get the numerical value for x, the equilibrium value for both A and B. After doing the algebra, you'll find out that the equilibrium concentration is 0.071 for both A and B. So our final values here at equilibrium. A is going to be 0.071. B is going to be 0.071, and the C that was given, of course, is the 0.5. Follows this problem a little bit easier because all equilibrium values are stated. This problem is emphasizing how to solve for x, and occasionally you can take the square root of everything and simplify things and allow you to calculate x a lot easier than if you actually had to solve a quadratic equation.